Hello, people. Hope you guys are doing well. Hope you had a long and restful, I guess, spring break. I'm not sure what that means, but I hope that's what happened. Let's get back to work. I just wanted to let you know that Josh came in today during office hours, and there was 2 exam ones, and so that changed the grades on some people on how they're doing in the class. So I encourage you to go in and relook at the grades because everything seems to be better now because I screwed up. I didn't realize that there was 2 copies of exam 1. Okay, so we're in chapter 6. And well, how do I start talking about chapter 6? We're going to start dealing with capacitors and inductors. I'm not sure what you learned in Physics 4B about capacitors and inductors, but I expect to teach you from scratch. I'll move a hell of a lot faster. And, you know, there's sort of like crossing the abyss right now is what you're going to see. Is that as soon as we get to the latter half of this chapter, it kind of reminds me of a climb in Yosemite. It's called the East Buttress of Higher Cathedral. So you get like the first 6 pitches. I don't know, a pitch is about 150 to 200 feet. You get through the first 6 pitches and you go like, God damn, this is like real easy. And then you get to this 6th pitch and you got to cross from one little edge to the other one. And you're seeing like 1,000 feet or so drop below you. And then you step across the abyss and you go like, shit, something changed. Everything above that was a hell of a lot harder. Okay, now that I'm encouraging you with confidence here, you're going to see that I'm going to go in, I'm going to review capacitors and inductors. And I'm going to tell you that sometimes I think I know what's going on with capacitors and inductors. And then I turn around and I go like, man, maybe I don't know anything about them. Capacitors and inductors are complicated. If you look at them very simply, what you'll find here is that there's not too much to them. But I mean, let me give you an example about capacitors, which I won't talk about in this class. All capacitors leak. That means that there is charge flowing through the insulator. Well, think about it this way. As a capacitor is charging up, its charge is changing. And because its charge is changing, there's a changing electric field across the capacitor. All of a sudden, there's a magnetic part to it, and there's a displacement current through it, which increases the leakage across the capacitor. Now, let me tell you, that's actually quite complicated. And, you know, this is what I mean here, is our job is not to go through those complicated details. Our job is to try to keep it as simple as possible. But there are times as we get into the differential equations, when you cross the abyss from, you know, having the hammer of node and mesh, that shit don't work here anymore. I mean, don't even look in that direction. The circuits that we're dealing with are non-linear. Resistors are linear. That means when we actually get to capacitor and inductor circuits, we have to speak in the language of differential equations. And I promise you, whatever you learned in differential equations is only going to lightly apply to this course now, because everything has to be derived from scratch. That being said, it is so much more interesting than what we did in the past. This is so much more interesting, and it's just so cool that you could go into the lab or into PSpice and model this stuff, and you go like, God damn, that's bitchin' what just happened right there. It is really, really cool stuff. Okay, that being said, let's charge ahead. Remember, we have a quiz on Wednesday and a homework turn-in on Wednesday. Okay, here we go. Let me find my OneNote, and here we go. Capacitors and inductors and initial conditions. So what you find here is that one of the very first things that you're going to struggle with is that we call capacitors and inductors are called let me be careful here. I should be more complete. They're called energy storage elements. Okay, they're energy storage elements. So that turns out to be a big deal here. And what that means here is that when they're called energy storage elements, what you're finding here is that that means that they store energy that can be retrieved later on. And this actually causes problems. You know why this causes problems? Because people think capacitors and inductors are active elements because of this. All storage elements are passive. And I know you guys are going to come back and you're going to say, no, they're not. They can be active. And I'm going like, no. In order to be an active element, you need an EMF. No capacitor, no inductor has an EMF working inside them to take charge from a low potential energy to a high potential energy. So they are passive elements. And guess what? It's going to cost you some energy in the future because you're going to think that, but you're going to say, oh, no, I could see the energy in these guys. I could see how it's flowing out. And I'm going to go, no, that's not what it means. So it's going to be a struggle for you. And the other thing that we should say here, which I already said here, these elements are not linear, like resistors. So this implies that they do not obey Ohm's law. And because they do not obey Ohm's law, this implies that you cannot ever use node and mesh for these circuits. You can't use mesh and node anymore. The only way you can solve these circuits here is if you use differential equations. Okay, that being said, we should start with capacitors. I could have started with inductors too. Capacitors might be a little bit easier to understand for some people. So let's go look at capacitors. Of course, there's an infinite number of applications for capacitors. right? There's so many possibilities. You know, you could use capacitors as flashes on cameras or keyboards. They act like capacitors. And what that really means here is that they have a very short RC time. And then you could have capacitors that in AC situations where they could, you know, resonate circuits like a radio circuit. There's a lot of stuff that goes into applications of capacitors here. So I'm assuming that you guys talked about all that stuff when you were in physics 4B. And if you're interested in more stuff about that, you could just come into office hours and we can talk about that. But for right now, what is a capacitor? Okay, the capacitor, what we say here is that a cap, right? I could say capacitor, it's common to call it a cap. A cap consists of two conductors closely separated. So that means they don't have to be parallel plates, right? You could look at some of these high capacitor values where they have very complicated surfaces, but they're very, very closely. So what you have to, the reason why they have to be close is because you want to cause induction from one plate to the next. That's the main reason. So it consists of two conductors closely separated, but insulated from each other. And what you find here is that probably a good picture of a capacitor here would be, we could imagine that we have two plates, right? This is the simplest model. And when you're looking at these two plates here, what you're finding here is that in between here is an insulator. Okay, so what you're finding here is that insulators we call it a dielectric. And what you're finding here is that when you look at this thing here, what you might remember here is that the capacitance is a constant. And this capacitance depends on two things here. It depends on geometry. What do I mean by geometry? I could have parallel plates, I could have spherical, I could have cylindrical, or I could have some other complicated thing here. So it depends on geometry, which typically means plate separation and area. Those are typically the two parameters that it depends on. It depends on geometry and the dielectric. So when I think about dielectrics, the way we typically write a dielectric here is that we have, so typically with not, this means in vacuum, but then we can multiply this by some constant. And so this guy here, so the wording gets complicated here, but for the sake of simplicity, I'll call this a dielectric constant. And that constant can have a range of values from 1, which would be vacuum, and then it goes up from there. So that's the way I define a capacitor. So typically we're talking about some plate separation, let's call it D. And then when I look at this guy here, then I talk about the area of the plate. So that's what I mean by a capacitor here. So what do I know about capacitors here? Well, I think one of the things that we should talk about is that how does current flow in a circuit with the capacitor? In a circuit with a capacitor. And I think that's an important thing here that we should really look at here. So what we're going to do here is that we want to do the following thing here. We want to go in and we want to start looking at a circuit that looks something like this here. So I imagine that I have a voltage source with the switch. Maybe not put maybe a switch like this. And so then I'm going to have my two parallel plates right here. And what you're going to see here is that there's my dielectric right in here. So my dielectric is an insulator, right? That's what we mean by dielectric. And what it's going to do here is that it doesn't allow charge to flow from the positive plate, the upper plate, to a negative plate. So one of the things that you're seeing here is that what I'm going to imagine here is that, of course, this is my source. This is my capacitor here, which is going to acquire some voltage here. So what you're going to see here is that as soon as I close this switch right here, what you're going to find here is that there's going to be some type of current flow. And I'm going to call that the current flow of the battery must be the current flow in the capacitor here. So what actually happens here? So I want to sort of like review here and talk about this. So no charge can cross the dielectric. How do I say this? No charge can cross through the dielectric in the cap. So what actually happens here? So what you're seeing here is that there's a couple of things here. We always assume that we have positive charge flowing. So as positive charge flows, what you're getting here is that you start off with neutral metal plates. So if I have positive charge flow, what you're going to see here is that I get a buildup of charge on the upper plate. Okay, so what this tells me here is that I simultaneously build up charge on the upper plate and you repel positive charge from the lower plate. So what that means here, as I have positive charge flowing in here, let's say that this is my positive charge. As it flows in, it's also pushing positive charge off the lower plate. And as it pushes positive charge off the lower plate, I then acquire a negative charge at the lower plate. So what we're saying here is that the rate of charge coming onto the upper plate is equal to the rate of charge repelled from the lower plate. So these two rates are exactly the same. So that means that the current, going to the upper plate must equal the current from the lower plate. So that means here that I'm getting current flowing in this direction right here. And what you're going to see here is that it is the battery that creates a constant current flow. But that's the way I want you to think about current flow through a capacitor. The rate that it's coming in, it's exactly the same as the rate that's coming out. So that's what I mean by current flow through a capacitor. Even though I say through a capacitor, there is no current flowing through the dielectric. It's before the dielectric and it's after the dielectric. Now, we haven't talked about time dependence, but that's what we really got to start to look at these guys here. So here's what we want to do here. So to understand, so there are three properties of capacitors that we need to know. Okay, three properties. The first one here is this. Let me make sure I'm saying this right. Is it 3? Or is it 2? I'm going to say it's 3. So what I'm going to say here, I might change my mind a little bit later, is that we should say this here. Capacitors act like shorts when completely uncharged and opens when fully charged. So that's one thing that we got to look at. We got to go in and we have to look at Ohm's law. So we need to go look at the so-called Ohm's law for capacitors. And then the third thing that we want to do here is that we want to look at the initial conditions of caps. Okay, so those are the three things that we got to really pay attention to. So here's what we say here. So we're going to say two things here. So what I'm really saying, capacitors acts like shorts when fully charged and opens when they act like a short when they're completely uncharged, and they act like an open when they're fully charged. So let's go look at this thing here. So the first thing that we want to do here is that this is what we know. I got to find my mouse here. So here we go. So the first thing that we want to look at is we want to look at capacitors fully uncharged or charged. So here we go. So if I start out with an uncharged capacitor, the moment a switch is closed, positive charge begins to flow. So we should start talking about language here. So imagine that I have a circuit with a switch, and then this is my capacitor right here. And so what I'm going to do here is that I'm going to close my switch here. Now, the moment that I close the switch, okay, so what we say here, so we really got to pay attention to language. So the first thing that I want to say with language here is that the first thing I want to say here is that the moment the switch is closed, we call that T equals to 0 plus. And at T equal to 0 plus, what you're starting to see here is that charge is going to start to flow. Now, I want to be really, really careful here, is that note that there's charges already in the wires. So the moment I close the switch, all charges everywhere start to move. And this is where it's useful to have a picture of my incline that I've shown you in the past here. So what you find here in this situation, I have what? I have an incline like this. And of course, this is ground right here. And what you're seeing here is that all of these charges are already on the incline. So as soon as I open the switch, you imagine that these charges are doing what? Sliding down the incline. And I think that's a pretty good model of what is actually happening here. So once again, the rate of charge flowing onto the upper plate is equal to the rate of charge leaving the lower plate. So what you're finding here is that what produces the fields in the wires, right, in a circuit, the field is not really a uniform field. It's a non-uniform field. But what you can do here is that you could break it up into smaller fields. Like, for example, I could call this point A, right? I could call this point, let's say A, and then I can call this point B. I could call this C, and I can call this D, E, F. Maybe I'll put F over here. And what you're going to find here is that the field in the wires, well, if you plot the potential function of these guys, what you see here is that if this is ground, I don't want to call that ground. Yeah, if I plot potential, and I want to be careful here. So this is going to be by label. not by, well, maybe it would be by position here. Let's say the position is X, and I want to be really careful with that position. So what you're seeing here is that when I hit the battery, what happens in the battery? I see a jump in voltage instantaneously. And this is where I go at point A. At point A, I'm going to have some value that's Vs. And it doesn't have a 90-degree slope. It's a little bit slanted here. And then what happens here is that I look at this guy, and then the field is changing here. And then it's going to be constant until you get all the way to, let's say, point C. And when I look at point D, you're going to see that somehow the field should have the exact same slope as before. So this might be D, and this might be sort of like F here. And then what you're seeing here is that the fields between A through C and D through F, because they're wires and they have a fixed resistance, you have something like that. But then the field that's polarized here actually, oh my, I did my picture wrong. Sorry about that. It should be steeper. I should have a field that's steeper, or that's now going to be F. And then the field across a dielectric is actually less steep. Maybe I have to draw it less steep. And it goes something like this here. So you have a linear field. And remember, what you're seeing here is that the slope of V versus X is equal to the electric field. So I should bring this down here. So you have something that looks like this. So when I say a uniform field, I got to be careful. It's not a uniform field. There is a change in slope as you go across a capacitor, because a polarized field gets reduced because you have the field of the parallel plates, and then you have polarization in the opposite direction that reduces that. So what I really want to look at is that what's happening, in these situations here. So now that I kind of give you a brief picture of how the electric field looks in a circuit here, what you're going to see here is that the field, that the E field produced by the battery and these things called surface charges on wires guarantees constant current flow. So these guys are going to guarantee that I'll have a drift of charge from the high potential to the low potential, where I'm seeing my current flow go from here and there, right? So this is the current flow here. This is the current flow there. Note, once again, there's no current flow across that gradient right there. So what you're going to find here is that now what you're seeing here is that at t equal to 0 plus, there is no charge on the plates. If there's no charge on the plates, then what we're seeing here is that the voltage of the source, right? That's not zero. The voltage of the capacitor is zero. So what you're finding here is that the potential difference between the source and the capacitor, this gives you maximum potential difference. And if you have maximum potential difference, then what this really means here is that the capacitor does not repel incoming positive charges. And acts like a short. So the highest current flow in the circuit is when no charge is on the capacitor. So, you know, there's lots of analogies. A lot of times people use the movie theater analogy, that when you first open the doors to a movie theater, there's nobody in the theaters. So that means you can occupy the seats at the highest flow rate. So you could imagine that I have a plate, right? Here's my positive upper plate here. By the way, I could do this with the lower plate too. It doesn't matter which plate. And so what you're seeing here, as if this is my wire right here, as I look at my charges coming in, these charges coming in, they do not feel a repulsive force from the plate. However, if I now have current flow, right? If I now have current flow and I now have a buildup of charge, so now I have charges here on the plates here, right? And what you're seeing here is that now if I have incoming charges, as these incoming charges are coming in, what you're going to see here is that these charges are going to feel what? An electrical force repelling. And so they essentially create what we call is an impedance. There's the flow rate has to feel something that's going to be different. So it's going to reduce. So now when charges are on the plate, the incoming charges feel the repulsive force. And it reduces current flow. So in other words, if there's no charge on the plate, I have a maximum potential difference. A maximum potential difference guarantees that in this case here, IC will be at a max. In this case here, IC is then going to be less than IC max. That's my point right there. So when there's no charge on there, you get maximum current flow. So now let's keep moving along here. So now that I have this, I'm going to say 4 here. So
Carlos,
now,
can I ask
yeah, go ahead.
In language sub bulletin 2, you said the E field from battery, surface charges, and wires guarantee a constant flow. Is it by constant flow? Do you mean like constant in that instant t equals
In that
0 plus?
instant, that the amount of charge flowing onto the upper plate is equal to the amount of charge flowing off of the lower plate.
Okay.
Yeah.
Constant across the two plates. Gotcha.
Yeah, just across the plate, because remember, we're only talking about the capacitor.
I think it's also worth pointing out, Carlos, that the slope, potential versus E field that you've drawn here would change when the capacitor loads. So there's a second one that's coming up.
Yeah, absolutely. But I'm really only thinking at that one moment.
Yeah, I mean that would be a sort of constant flux until it's full.
Right.
But I think it'd be worth like sort of sketching it when it's full, just for comparison.
Oh yeah. Oh, by the way, I will. I'm trying to go through this very methodical because I don't trust what you know about capacitors and inductors right now. And if you don't have it down, you're going to really get your ass kicked in 7 and 8. And I don't want that to happen. That's why I'm spending this extra time. Most of the time I'd go like, okay, you saw this in 4B, let's move. And I'd be like done with this already. But I want to do it right. Okay, let's keep moving here. So what I'm going to do here is that, so now what, just reminding you what Jason just said here, I should, let me erase this and make a statement. Remember that with capacitors, the current flow is always changing as a function of time. It's always changing. And you can see this by the picture on the right here. If I have charge, as I put more and more charge onto that plate, you're going to get a stronger repulsive force, which makes it harder for the electrons to get onto the plate. So when I'm talking about current flow, I'm really trying to stress I'm talking about an instant in time, and that current flow is going to do what? That current flow is going to get smaller and smaller, and the slopes of these things are going to get less. And I will bring that up here in a moment, but it's always changing. So when I'm talking about current flow, so this discussion is only about the instant of time in order to make sure that you understand if there's no charge, it acts like a short. And then you're going to see that as charge builds up, there's a point where it's going to reach maximum. And that's what I want to talk about next here. So when I look at my fourth piece here, as charge continues to build onto the, let's say, upper / lower plates, it gets harder and harder to to place charge onto the plates. And the reason why, once again here, is because of the repulsive force will get so large here. At some point, the charge flow will completely stop. It gets so large that no charge will be able to come. So there's two pictures that we can draw here. So the first picture here, which might make you feel a little bit better, is that if I have a parallel plate like this, and then of course this is my capacitor, what you're seeing here is that there's going to be a repulsive force from the plates. And then there's going to be the force of the battery and the wires that's going to be in the opposite direction. So in this case here, you're going to see that the net force acting on charges is going to be 0, because then you're going to find that these two are equal and opposite. And because that's equal and opposite, this tells you that you stop current flow. But we don't like the language of forces, right? That's Newton's second law. And that's just a crappy picture to actually deal with. The picture that we want is we like the language of energy. And the language of energy is voltage. And what we say here is we say the following thing here is, but in the language, what's actually happening here? So remember my picture beforehand. Here's my battery, and here's my plate. And so when you're looking at this plate here, what you're finding here is that in this picture, this node up here, this is the node VS. And this guy down here is the ground. So in this picture, I have current flow. I see going like this. Why do I have current flow? So I have current flow because VS is greater than VC. Okay, so where this guy right here is VC. But as I get more current flow, what actually happens here? I'm going to copy this picture here. What happens is this starts to happen. What happens is the capacitor starts to move to a higher potential. So you could see here, remember, how do we measure potential? We measure everything from the ground. So if you look at this here, this represents the height of VC, and this represents the height of VS. So if I compare the first case over here, you could see that this is a smaller VC. And so what you're finding here, as I continue this picture here, at some point, the capacitor gets enough charge in such a way that now what happens? The capacitor's height is now at the same height as Vs. And because the potential between the capacitor and the voltage source is exactly the same, then we say that V, the potential difference between them, is now zero. And it's now zero implies that there is no more current flow in the circuit. And because there's no more current flow in the circuit, this means here is that a fully charged capacitor acts like an open. So when I look at my circuit, I can replace the equivalent
You're muted.
Did I just lose you guys?
For a minute.
Okay. Ohm's law for capacitors.
It's also
And your
not screen sharing anymore, Carlos.
God damn it. Okay, so I want to now start talking about Ohm's law for capacitors. So here's what we know is that we have to define the capacitance equation. So starting with the capacitance equation. And what's the capacitance equation? Well, we write capacitance, right, as C, and this is actually equal to the charge of the capacitor divided by the voltage of the capacitor. And so the units of capacitance are farads, which is typically written as F, and usually they're in micro or picofarads. So this is our main equation for capacitance right here. Okay. So we've been talking about current flow through a capacitor. So to get current flow through a capacitor, we take the derivative of C. And the way we do that is if I rewrite this, note that this becomes Q is equal to C BC here. But capacitance here is a constant. And remember what I said before, the capacitance only depends on geometry and the dielectric constant. It doesn't depend on anything else. Okay, doesn't depend on anything else. So what we want to find here is that we want to do the following thing here. If I take the derivative of this guy, I know that the charge is changing as a function of time. If I have more charge, I'm going to have more voltage. So then this implies here that if I now take the derivative, I'm going to get dq dt. But by the definition, though, this has to be the current of that's flowing through the capacitor. Remember, it's not through the capacitor, it's before the plate and after the plate. And this guy is going to be C dV dt. And this is one of the main equations for the rest of this chapter. This is what I call the capacitor equation. And of course, you got to memorize this, dude. I mean, it's not that hard to memorize, but this is the Ohm's law for capacitors. This is a super, super, super important equation here. And you could see clearly the difference between resistors and capacitors, right? This is a relationship between current and voltage. And you can see here, it's not linear. It's a differential equation. It's not linear. This is the reason why you cannot use mesh or node anymore. Whereas when you had mesh and node, it required the current and the voltage to be related. But what you're seeing here is that what this is telling us here, it's telling us here that the capacitors have a time dependent behavior of the current / voltage. It has that time dependence here. And so if you go and you were to actually look at this thing here, let's try to interpret this thing here. Okay. So what I'm going to do here is that I want to interpret this thing here. So let's interpretation here. And the first thing that you see here is that if you go and you do this, we know for starters here that we have an RC behavior. So if I plot an RC circuit, what you're going to find here is that it looks something like this here. I'm going to have a curve. So if I look at this curve here, what you're seeing here is that this curve, let's say that this value right here is my VS value. I'm going to be plotting VC as a function of time here. And what you're going to see here is that my curve, what does my curve actually look like? Well, my curve, assuming that I start with an uncharged capacitor here at t equal to 0, it actually looks something like this. And so what you're seeing here is that this curve is this blue shaded area that I'm showing you here. And what do I actually see right here on this thing here? So the first thing, if I plot an RC, what you're seeing here is that there's a couple of things. The first thing is that if a capacitor is fully charged, VC is a constant and there's zero current flow. So a fully charged cap implies that VC must be VS, which is a constant. But wait a minute. Note that the current is proportional to the slope of VC versus T curve. In other words, IC is proportional to the slope of dV dt here. So if I look at when it's fully charged, look at the slope here. The slope is what? Is flat. This tells me here that IC is 0, and this is what? This is a fully charged cap, just as expected here. Now, what does it mean when I have so what happens if I have an uncharged capacitor? An uncharged capacitor implies that that the potential difference between VS and VC is maximum. So that means that I have maximum current flow onto the plates. Right? I have maximum current flow. So when I look at this thing, look at the slope. The slope here at t equal to 0, that's maximum slope as it goes along here. And you could see that if I come in here and I look at this slope right here, you could see that that slope is less. So what you're seeing here is that right in here, I'm going to have rapid increase, whereas as I come along here, like in this spot here, I'm going to have small increases. So again, this is telling us that this curve is telling us exactly what we talked about beforehand here. So that's what that curve is telling us here. Now, there's another little thing here that I think is quite interesting here, is that if one shorts out a capacitor, what does this mean here? What happens to the voltage? Well, what I mean by this is that this is what I mean by a capacitor here. So typically, when you look at a capacitor, what does a capacitor look like? I could say that if I think about a radial capacitor, and what you typically have here is that you have two wires. If it's a polarized capacitor, what you find here is that what I do here is that when I say, what I do here is that I start off with a charged capacitor. And then what I do here is that I short out the capacitor by connecting the two wires. And so what actually happens when you do that? Well, if I look at the current flow, so what I want to do here is, the question is this. If I do that, then what I'm looking at here is I want to look at the limit of IC as delta T goes to 0. And what this is really telling me here is that the limit of this guy really means that I have Z dV dt like this here. And you can see that in theory, as T gets really, really, really small here, that means I have a very short time to take a voltage of a capacitor and effectively bring it to 0 very, very, very quickly. I discharge the capacitor. You could see that this gets very large here. Now, an application of this could be the spark plug that you have in your car. So if you think about your spark plug in your car, I mean, your battery's 12 volts, not really, but maybe 12.6. And what you do here is that you can actually, you have a little tiny gap. And if you close a switch, you can go, you think of your car battery, putting out 12 volts, but you could get thousands of volts across a spark plug because of this. And you're getting this really large current. So what happens between the two wires? So when we're saying a very large current, is that what we're really saying here is that you're really getting what? It could be so large that you get dielectric breakdown. Now, dielectric breakdown, right? So for a millimeter, well, dielectric breakdown, you may remember dielectric breakdown is 3 million volts per meter. But if you think about a millimeter, so you could imagine that if you get a gap, if you have a high enough voltage and you get that gap to be smaller than a millimeter, you're going to get thousands of volts across that little gap. And as a consequences, you can get a spark to fly, dielectric breakdown. But the capacitor equation is explicitly telling you this thing right here. Okay, let's move on to the last thing here, is that we want to look at the initial conditions. Okay, and here's what we find here. So now we want to look at the initial conditions of a capacitor. Oh, I shouldn't call, man, you know what? let's see, what did I do? I did 2, then I started calling these 1. Do you know what? I'm going to come back and change this to I, and this to double I, because I want to call this 3. So I follow the things that I said before. So here's what we know about capacitors.
Carlos,
Yes.
I'm forming a question here. Where is the voltage? Where is the increased voltage coming from? Your analogy to the spark plug, I think, is not accurate to how those systems work. That's induction.
No, I agree. But if in the old days, they used to have a switch with the capacitors. You're right, they use inductors now. But in the old days, they had a switch. And so if you were to apply this to a switch.
So I've seen John take a screwdriver and put it across that cap the size of a beer can. Yeah. And sure enough, you get a huge spark, but I'm not seeing where the increased voltage is coming from. I thought that spark was due to a high current.
So you got to be careful here. So you're talking about a capacitor that's not connected to an outlet.
Yeah, totally.
Say that again?
Yeah, just a charged capacitor.
Just a charged capacitor. So you can do this thing right here. So if you want to look at, if you look at the old school.
So yeah, dVc dt is huge.
Yeah, so what you do here is that you do this here. So you already have a voltage across the capacitor. That's the source right there. And you have it so that it's now fully charged. So now what you do here is that you open the switch very, very, very quickly. And if you open the switch very, very quickly, right between, so as soon as you're open this thing right here, what you're going to get right in here is that you're going to get that spark to flow right here. And that's that dielectric breakdown that I was suggesting with this old school spark plug. I agree that modern day spark plugs are inductors. Yeah, you get that spark right there.
So is the voltage across that gap ever more than Vs?
Remember, it's not about Vs, right? It's not about Vs. It's about how quickly, maybe I should say that. It's, God damn it. How quickly it's disconnected. Right? It's about how quickly it's disconnected. With the inductors, it's the exact same thing. Right? So here, you're interrupting the current very, very, very quickly. And then you get the big spark. But you will get current flow between 2 terminals just because you're changing the voltage very, 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 very quickly.
The capacitor resists changes in current.
No, the capacitor resists changes in voltage.
And the inductor is current, right?
But the current can change instantaneously. And that's exactly where I'm headed towards right now.
All right.
Yeah, these are all demos, by the way, that if we were I used to do them in person in 4B all the time. I would just say, what? Check this out. Yeah, you can get shocked by capacitors as well as inductors. In fact, the inductor, in my opinion, they're much easier to get sparked, get shocked with. Oh yeah, dude. I got so many students. I tell students, don't do this. And then of course, you see people in the back of the lab room going like, I wonder if Carlos knows what he's talking about. Then I see them get, shocked, and I could see that little jerking motion of their body. And then I point them out and I start laughing. I go, you dumbass, I told you not to do that. Shit, I don't care. I mean, go ahead, do it on your own time, not on my time, because if I have to write up a report, I'm going to be pissed. Okay, moving on here. So what you're going to see here is that there's two behaviors, okay? The time factor to remove charge from a capacitor, right? So there's an issue here. Capacitors have have voltage limitation on how quickly voltage can change. And so what we say here is that the voltage of the capacitor at T minus must be equal to T plus. In other words, the voltage cannot change instantaneously. And the way to see this here, if I can just come up here and just kind of grab this thing, it's really in this curve. And I know it may seem like I'm cheating a little bit, and I am cheating a little bit. And what I'm really saying here is that when you look at any one time here, right? If I look at this point right here, that means if I throw a switch here, that the voltage, let's say that this is the time that I'm going to throw the switch. So right before the switch is thrown, let's say this is T minus, and then right after the switch is thrown, those two voltages must match up. However, the currents of the capacitor in general change. So what I'm saying here is that current can change instantaneously. And what I mean by this thing here is that what you'll find here as an example of this thing here, let me block this off because this is an important one. I mean, by the way, this is mostly the chapter that we want to focus on right there, is those two things right here. And what you're going to see is you're going to see the following thing here, is that if one has a fully charged cap, IC is equal to 0 in that branch. So when a switch is thrown, the current goes to 0 to some non-zero value instantly. That's if you have a fully charged capacitor. And those are the things that we want to focus on. So on Wednesday, you see, I spent the whole lecture on a capacitor. I mean, I'm going to have to make up for time later on because I'm going to need that time. But I felt like we really had to go through them in as much possible detail as possible. Okay. I will see you guys tomorrow. So remember, I'm going to do P-Spice. I don't know if I said this earlier. I'm going to do a P-Spice lab tomorrow. By the way, I found out when the oscilloscopes are coming in. They're coming in sometime in the first week in April. I just found out on Thursday why I couldn't get any information is that the order does not say Cabrillo College. It says the warehouse. And then it gives the address of the warehouse in Aptos. So that's why I had such a hard time tracking it. But they promised me that it's supposed to be here first week in April.
It must have gotten stuck in the Suez Canal.
Yeah. God damn it. Could you imagine if that's the case, we're up shit creek. Yeah, that's all I know. Okay. I will talk to you guys later, okay? Bye.
See you, Carlos. Thank you.